Our seminar speaker today is Dr. Sarah Bentley. So Dr. Sarah Bentley is an assistant professor in the solar and space physics group at Northumbria University. They completed a PhD at Reading on the solar wind driving of magnetospheric ultra-low frequency waves, and has recently been investigating the effects of those waves on radiation belt particles, both to understand the physics and to capture the effects in space weather models. Due to an undergraduate degree in mathematics and a year spent working on software coding of geometry, Sarah is also interested in finding and developing techniques specific to the challenges of a complex multi-scale magnetosphere. Finally, they're actively involved in research about the experience of minorities working in the space sector. As a result of this, Sarah tries to reflect on the approaches in scientific research and embed this in their practice, from supervision to paper writing. And Dr. Bentley is happy to talk about any of these topics, should you wish to discuss them with her. And so I will now hand over to Sarah to give a seminar on how do fundamental modelling choices affect radial diffusion in the Earth's radiation belts. Thank you.
Right, so thank you for that introduction. Now that I've heard you read it, I realise I gave you quite a lot of difficult syllables to put one after each other. But yeah, thanks anyway. Thanks for inviting me. So today I want to talk about Earth's radiation belts and how we can simplify or approximate long-term behaviour using just one of the particle motions. And then finally, I'll be talking about some of the work that we've been doing on that and some of the unexpected results we've seen that we're still trying to understand. So just to get everyone on the same page, Earth's radiation belts are some high energy particles that are trapped by the Earth's magnetic field. So they're all in one relatively nearby region of space. And you'll often just see these described as two separate belts. So there's an inner belt, which is relatively stable and made of protons, and then an outer belt, which is highly variable, much wider ranging in extent, and has energy ranging from kilo electron volts to mega electron volts. So to give you an example of the variability, got a video here of 1 month from the Halloween storm in 2003. And you can see right now what's happening is that they're really changing in energy and extent, like really quite drastically. And that's some of what makes the radiation belts interesting, challenging, and also having such a impact on space weather. So I thought I'd pick out a couple of reasons why the radiation belts are interesting. So one of them is that because this is there are no collisions in the radiation belt region because there's so few particles, this means that energy and momentum, etc., can't be transferred through collisions, so everything happens through wave-particle interactions. But in this region of space, there are so many different wave populations that lots of interesting things are happening, and it means that our physical intuition, which is often built on how air works, which is again collisions, doesn't really make sense, and so they're just inherently weird. Well, I think so anyway. And the second reason for them to motivate some study of the belts is the space weather. So you've probably all seen this figure or one similar with all the different areas of space weather, but radiation belts affects this part over here. So you've got energetic particles from the belts affecting spacecraft. So particularly you've got single event upsets and electric charging. So for the single event upsets, this can affect the mechanisms for moving the spacecraft around, but it's not just single one-off incidents that have an impact, but what this environment means for the satellite design, for the lifetime. And in more recent times, now that to get spacecraft into place, we use something called electric orbit raising. They spend much longer in a more dangerous region of the belts. And this means that if, whilst you're putting a spacecraft in place, there happens to be a storm, then it could wipe out half the intended lifetime in one go if you're very unlucky. So there's lots of operational constraints to do there as well. So I've said that the radiation belts are made of very high energy but relatively few particles. And because they're so high energy without collisions, we often say that we can treat the radiation belts as if they sit on top of the rest of the magnetosphere, with the underlying colder plasma affecting what the particles do, but without the particles themselves then feeding back in too much to the plasmasphere. And yes, this is an approximation, and to me, this is where the distinction between the ring current and the radiation belt lies. I mean, everyone you ask will have a different answer, but for me, where you can kind of approximate what's going on as a separate bubble where the magnetosphere feeds in but it doesn't feed back, that's where I would say a radiation belt approximation is valid. So to model these particles, we can use some kind of numerical modeling that's very physical, but this tends to be very expensive. So we might use that to test the theory behind the radiation belts, behind our longer term models, but we wouldn't necessarily use that to do longer term modeling tasks like forecasting or trying to understand what happened over days, weeks, months, or years. So instead, what we would use is a diffusion modeling, and we can use this because of certain convenient facts about the motions of the particles in the radiation belts. So here I've got just an example of a diffusion or heat equation, and I wanted to put this here to emphasize that, especially for this constant coefficient, which is not what we have here, not what we use in the radiation belts. This is a very, very well-known equation. There's lots of information and knowledge out there about how to use this. So we take advantage of that. So the three particle motions in the radiation belts that are relevant start with one that you will have learnt during basic electromagnetism lectures. So if you have a particle in electromagnetic field, it will gyrate. Okay, and so this is what we see around each of the magnetic field lines. You'll see the particles gyrating around the field, but you'll also see as they start to set off in one direction, they will get closer to the Earth, and then as the magnetic field gets stronger, it'll bounce to and from pole to pole, and this gives you your second particle motion, periodic particle motion. And finally, as you've got this bounce and gyro motion, as the particle is actually traveling over variations in the magnetic field, those result in a final drift around the Earth with protons going one way, electrons going the other, and that is the third periodic motion. Right, and in classical physics, I'm not going to go into detail about how that arises, but if you're moving adiabatically, so in a relatively slow and reversible manner on a periodic path, there's a conserved quantity that's associated with that motion. So, for example, the gyro motion is associated with the magnetic moment, and you also have conserved quantities related to the bounce motion and the drift. What if things happen on the timescale of the motion, then that quantity isn't going to be conserved anymore because this idea of it slowly happening is broken, right? And that underlies all of our diffusion modeling. So what I want you to notice here is that you've got the gyro motion and the bounce motion are on a much smaller time scale than the drift motion. So here I've put tens of seconds, but that's like kind of the highest that you would actually expect, like minutes, hours even. And so that means that although we have to treat these two together, we often make the approximation that for the longer timescale stuff, we can just talk about conservation over the drift motion, and that gives us our radial diffusion. So when you're drifting around the Earth, the conserved quantity related to that motion is actually the magnetic flux, which is contained in a drift orbit. But instead of calculating that magnetic flux, if we're just thinking at the equator, then what we can do instead is look at where that drift orbit intersects the equatorial plane. And so to make this description more tractable, we can say, okay, relax whatever magnetic field we're in now to the dipole magnetic field, and then say that the distance of this drift shell in that dipole magnetic field is going to be going to exactly correspond with the magnetic drift flux. So what we can do is then talk about how the drift shell is conserved, the radius of that drift shell in a dipole. I mean, there's a lot more nuances there, but that is a very efficient way of thinking about it. So if you think about an individual particle, then what does it mean for their drift shell to be for this L star, for this drift shell to be broken? So if you have an individual particle going around and you have, say, a pulse or a change in the electromagnetic field, maybe it's going to get kicked in some way that makes it change to a drift shell that's further away or closer to the Earth, right? So in this example here, if you've got two particles that start with at P, if you've got two particles on the same drift shell to start with, and by the time they get to P, one of them encounters this pulse. Maybe it changes to a different drift orbit, but by the time the second one gets there, if that pulse doesn't exist anymore, then maybe that one stays on the same drift orbit and ends up at Q star instead. And so what is then happening is because that pulse existed on a time scale that's shorter than the drift period, you've got the L star of those two particles is no longer the same. So we've broken this symmetry. And so what this means is that we can track changes in this L star across the population to track what's happening to the particles. So this was an example of one or two individual particles, but by showing the distribution across L star using a diffusion equation, we can track what's happening to the entire distribution. So that's what this figure here corresponds to. So in this numerical simulation, you've got some ultra low frequency waves, which happen to be on the time scale that's relevant, acting on some particles that all start on one drift orbit. And you can see that over time, some of these particles are getting moved to drift cells, which are either closer to or further away from the Earth, and they're spreading out in this L star or L. And that's what we mean by radial diffusion, it's that diffusion across L. So how do we model that? So in this diffusion equation that we use here, what we do is we average over the drift orbit, and so we only need to take one radial coordinate L. So what this means is that for long-term approximations, we can use a one-dimensional diffusion equation to approximate the entirety of the radiation belts. So as well as my interest in the ULF waves and their effects on the particles, that means that this is a really useful test bed for radiation belt techniques. And what I want you also to notice here, that all the physics of the electromagnetic field that is causing these changes in the particle motion is contained in this diffusion coefficient, DLL, right? So that's all the physics then has to go into there. So that means that a lot of work goes in to try and to identify what these diffusion coefficients should be. So this might seem like a little bit of a tangent, but this is the final step to set up our most recent study. So in general, especially for space weather, but this comes from terrestrial weather forecasting, ensemble modeling is used to capture some of the uncertainty in a physical system or in our modeling of that system. So what we might do is vary some of the initial conditions or vary some of the other parameters in the numerical simulation. And then by running all of these, you can get an idea of the uncertainty of your forecast, but also try to represent some of that uncertainty which is inherent in any kind of physical system. And for radial diffusion and for the radiation belts, I mean, I've already shown that video of the Halloween storm. There's a huge amount of uncertainty that's there for us to represent. And if we look at especially a radial diffusion study a few years ago by Rees Thompson, he added in some variability in the diffusion coefficients and showed us that when you include that variability, you can get some very different final distributions of the electrons. So what I want you to pick out here is, I know it's not very clear, the black line, this black distribution is what you would get if you ran radial diffusion just using the single deterministic diffusion coefficients. On the other hand, if you vary those diffusion coefficients by the amount that we know that they vary, then you get the kind of distribution shown in all the colors, and you can see that the fit of the average final distribution is not the same as what you get if you don't include this uncertainty. So we need to take these techniques even just for the radial diffusion. So what we've done in this more recent study is to try and look at some of the fundamental settings to understand how we can use ensemble modeling and how choices in our model will affect interpretation of those ensembles. So this was supposed to be like a pilot study to start it off, but of course it became more involved than that, and there was a lot more to understand than we had initially expected. And I should say that ensemble modeling isn't the only way to deal with uncertainty. Like, you can use probabilistic approaches, you can use data assimilation, and people have done those. It's just not really what I'm talking about today. So some of the initial goals of our study were to use the simple radial diffusion approximation to kind of explore this, how to use ensembles in the radiation belts. If we want to use ensembles, what should we measure between ensembles to compare the ensemble members? How should we measure it, and what does it mean when they vary? How much of each variation is due to physics that we're representing, and how much of it is just due to modeling choices that don't necessarily represent the physics? So we investigated quite a few model choices, including the initial condition and an enhancement in addition to a background population, the location of the plasmapause, and some of the outer boundary settings. Right, so to set up our numerical experiment, we have this diffusion equation. which I showed on a previous slide, and we've run our numerical experiments with and without loss. So when we include loss, it's just 1 over an electron lifetime. 1 over an electron lifetime, and this is meant to represent some of the loss you would get if you were including those, if you were actively including those higher, faster effects. So it's loss from pitch angle scattering, and this the diffusion. Oh, sorry, I did not add it onto the slide, but this we do this using the Crank-Nicholson method to try and to make sure that we can change the diffusion coefficient in time and in space, because that is an important component of the radiation belts, is this changing diffusion coefficient. And what one of the themes underlying this that we'll be talking a lot throughout my results will be the how this diffusion coefficient depends on L. And like where you are in the domain, the amount of diffusion changes. So the other important component about the setup is this initial condition. So the initial phase space density, the initial particle distribution is you have some background particles and an enhancement, right? And so we've just got a little bit more information about each of those components. So for the diffusion coefficients, we actually run numerical experiments primarily with diffusion coefficients which are used in practice for modeling. So these are, you calculate the magnetic component and the electric component, and then you add them together. And these are from derived from data by Louis Ezeki. And what I want you to note here is that they both depend on L and on Kp. So the Kp represents how active is the magnetosphere, and therefore how strong is the diffusion. And then for some of the later experiments, we actually need a more idealized and analytic description rather than just an empirical fit. And that's when we have to use this diffusion coefficient here. And to explain how we vary the initial condition, we have the Gaussian, or the enhancement is represented by a Gaussian, which is centered at a mu and has like a width or variation of sigma, whereas the step itself is represented by a step size b, and then by like where the enhancement is as well. And so we vary all these parameters to see how they affect ensemble runs within a week. And now I've got a boring list of all the things that we vary. And I'm not going to talk about all of these, but I'm just going to talk about some of the most interesting. So some of the ones with the most interesting results included the location of this enhancement. So where in our L's, I'm saying L because it's much easier to write and then include subscripts, superscripts, etc. in papers, but I mean L star. So where is this enhancement in our domain in L? How high is the step size? Where do we set the outer boundary of our simulation, and what is the condition on that outer boundary? So I'll go into more detail in that when we get there. And also, where do we set the edge of this loss? So where is the plasmapause, essentially? So far, we've talked about the model setup, but not about how we compare the ensemble members. So we found that you can't use any of the measures we were hoping to use, like not that we were hoping to use mean square error, but you can't use something like mean square error very easily, because you then need to set a threshold for when either two distributions are close enough to be counted as the same, or how close they are to equilibrium. And we found that our results became then dependent on the threshold more than anything else, which didn't help any of our analysis. So to counteract this, we came up with two different measures, two different metrics. And the first one is something called time to monotonicity. And this is a morphological metric in that we're interested in the shape of the distribution. And we picked this because it's actually related to some of the physics we're interested in. So quite a lot of the time, if we're trying to model the radiation belts or radial diffusion, is how long is radial diffusion interesting for? How long is it affecting the evolution? And when you're talking about time to monotonicity, it's how long does it take for an enhancement to diffuse away and leave you with just essentially a background. And so we are measuring the time it takes to get a monotonic distribution. So a monotonic distribution might be the background rather than just the bump, the enhancement. It might be this same shape, but reduced, or it might be zero everywhere, right? Because you've got particles at one side, you've got nothing at the other side. So monotonic is always going to mean those options. So some results. Just a first set of results to show you how time to monotonicity worked for us. So we've got two of the parameters I showed you in our experiments here. So we've got the location in L of the enhancement, and we've got the step size B, which represents how the amount of background particles. So what you can see is that for each Kp value, we were finding that as an enhancement is placed or located at a higher L value, it diffused away more quickly. We reached monotonicity more quickly. On the other hand, the higher the step size for any Kp level, if it were higher, then we were reaching monotonicity more quickly as well, right? And these are pretty sensible on reflection, especially if you recall that our diffusion coefficient depends on L. So you have an L in front of this power to the 10, but also in the exponent as well. But what is actually happening turned out to be somewhat more nuanced than we were expecting, especially once you start comparing what the outer boundary condition is. So in the figure A here, we've got a diagram of what's happening to the particle distribution if the outer boundary is set to be at a constant gradient, right? So the particle level at the outer edge of our simulation boundary then keeps on going, right? And that's to reflect that the simulation domain is a fairly arbitrary cutoff. It doesn't include the rest of what's going on in the radiation belt, so those particles do continue to exist. And that means that when this evolved to reach monotonicity, yes, you have this enhancement diffusing away. It's being acted to reduce gradients to go towards monotonicity, but this flat part here is rising up to make a plateau, right? So to reach monotonicity, if you have this Neumann outer boundary, your final distribution is going to look like this. On the other hand, the other option we had for our outer boundary condition is to set this value at the outer boundary and say whatever wants can go in and out, doesn't matter, but this value, we know what it is because it represents a data point that we've observed. So that's not allowed to move. And for this to reach monotonicity, material can move out of the domain, but this value can't rise can't increase or decrease. And so we have to wait for the bump to diffuse away, and the final distribution we reach is then much, much lower compared to if it were a Neumann distribution. And so the reason why I put this slide after the previous one is this helps explain what's going on with that step size. If you have a higher step size, you're already much closer to reaching that monotonic state, no matter what your outer boundary condition is. And I should say I'm going to talk about loss a little bit, but loss is a bigger factor than this, which is good because this is very fiddly. And I'm also going to talk in a bit about what this actually means for the outer boundary conditions that we want to use, because you can motivate both of these physically, but quite clearly they're very different, and that means that they can't both be right. So far we've got this morphological metric to tell us, to try and help us compare to two ensemble runs or even multiple runs in an ensemble. And we've seen that because the diffusion coefficient depends on where you are in the domain, the system actually evolves differently depending on where you put everything. And we've also got some problems with the outer boundary. Not that we didn't have them before, but they're new and more fiddly. So which of these is right? And to answer some of this, we have an additional way of measuring the ensembles. So this is where we start to use more analytical tools. So we have mass and energy light density. So the two main ones to focus here are these equations. So first of all, we take the particle distribution and integrate it over our domain. So we've got a 1 over L squared here to represent the change to our radial coordinate system. And this tells us how much mass is there in each experiment and how does that change over time. So you might remember from either stats or from physics, statistical mechanics, that this is actually a first order moment, and you can take the second order moment by integrating over the square of the particle distribution. Right, and what this gives us is like an energy-like density. And to try and understand, to build an intuition for what this epsilon, curly e, means is it's how close is this distribution to a zero state? Like how long would it take for the entire distribution to diffuse away? Okay, and this is also where our second idealized diffusion coefficient comes in. So if we have a nice form of the diffusion coefficient, then that means that we can actually differentiate these and see how the number density and the energy density change over time. So I'm going to give you, before we start talking about that, which is actually some of the most interesting parts of it, I'm going to give you an example of just using the energy density itself. So if we track this energy-like density, energy-like density over a week, then we can see that if we've run this example for both Neumann and Dirichlet outer boundary conditions. So the blue ones are where you have that constant gradient at the outer boundary, and the orange ones are where you have that constant fixed value. And we've also run it for a different outer boundary location. So one at 6.5 Earth radii and one at 7.5 Earth radii. And you can see that throughout the simulation, they're all decreasing in this energy light density, which makes sense because we're not adding any more stuff in, it's all gradually diffusing away. But after a few days, depending on what your outer boundary condition is, some of them are going towards this equilibrium state much more quickly. And also, depending on where you put this outer boundary, the rate at which you move towards this equilibrium state is also changing. So it involves both of them. And this is, well, it's fiddly. I guess let's go with it's fiddly for now. So there's no clear outer boundary condition or outer boundary location, but they evolve differently. So which is the right one? So here's just a very short component of the arguments, the thoughts that we've been going through to try and answer this so far. So this is still very idealized, right? And in practice, models drive the outer boundary with real data, not just one single point that they haven't changed. So maybe this captures everything that's going on. On the other hand, to do this, you have to cut to where the data is. And in practice, this turns out to be quite a way short of where the actual edge of the radiation belts are. So this means that we're cutting off the part of the domain where at highest L, where the diffusion is happening most, and this changes the way the system evolves. So maybe this will be okay for modeling or hindcasting, but will it work for forecasting? So I mean, the major question here is when we actually have data, how well does it work to cut short the domain and use that data? And luckily, early last year, someone ran a set of these experiments using data. So cutting short the domain, if you cut short the domain to have that real world data, it massively outperforms having an outer boundary that reflects that actually the particles keep going. The radiation belts are further out than that. So to model previous observations, that's great. Using the data is better. I still don't really know where this leaves us if we're trying to do forecasting, because if we're forecasting or if we're trying to predict what the belts are doing, we don't have that data yet. So what should we do? And also, can we use maybe data assimilation or something to put this data point inside the domain and include more of the diffusion? Yes, this is one of the major thinking points that we had out of this. And now I've called this slide a bonus, but it's not really. I shouldn't have said that because it's kind of one of the major reasons of using this energy light density is that we can calculate the rate of change of the energy density. And if you were to do this for a simple diffusion problem, so for if the diffusion coefficient were constant everywhere and you're in a Cartesian coordinate system, then you'll find that the rate of the change of the energy light density is just the gradient squared. And so what this means is that diffusion acts to reduce gradients, which is accepted knowledge. But if you do this for radial diffusion, I mean, we get some things that depend on the boundaries, which is fine. You know, if you lose more out of the boundaries, then you've got less to lose. That's pretty obvious. But it's this reconfiguration term, which is the equivalent of the above, which is different. So you notice that you've still got the gradient of the particle distribution here, but you also have this term, which is the diffusion coefficient and L. So because this diffusion coefficient depends on L, does the whole distribution move faster towards this zero state or an equilibrium state due to the gradients or due to our diffusion coefficients? And so by calculating each of these, so by calculating the gradients and calculating this term here, the diffusion coefficient divided by L squared, we can compare those two and see which ones correspond most to changes in how fast the system diffuses away to nothing to an equilibrium state. And here, what we've plotted is a ratio of the gradients to the diffusion coefficient term. And red means that the gradient component is bigger than the diffusion coefficient component. And what you can see here is that these are all red. If you were to fiddle around with these a little bit to try and run more experiments to say, is this really right? You do start to get some blue components at much higher L, or in when you're starting out with our initial condition, because it's not quite right. But actually, we find that gradients have more impact than diffusion coefficients everywhere. So yes, diffusion still acts to reduce gradients. But it's not that simple, because if this is true, this current understanding of how we do radiation belt modeling is that the diffusion coefficients are the most interesting part, not just because they contain the physics, but because they change what goes on in the system. And having talked to a few people about this, they still believe this is to be the case. And so if these results are reflective of reality, it would mean that we should be spending much more effort looking at the particle distribution and working out what the gradients are to see what's going to happen than the diffusion coefficients. On the other hand, if everyone else and their combined expertise over modeling the radiation belts for many years are correct, then this is wrong. And it's probably because we've only got the radial diffusion component, right? We haven't included the other parts. Like I said, this is an idealized experiment. And it might mean then that we can't use radial diffusion just as an approximation. So either way, this is going to be interesting, but we don't know what it means yet. Right. And just finally, before I wrap up, I did promise to talk about loss. So if you add in loss, all the outer boundary condition and location, the initial condition stuff, you do still see these effects, but they're not as strong as the effect of this loss, which is good because it simplifies everything. It means that further on down the line, when we've improved our radiation belt modeling, we'll probably still want to look at these, but maybe not yet. Maybe we've got other things to do first. There is one nuance I wanted to bring attention to, and that is if you include loss but put the plasmapause further out than the location of the enhancement, then over time you find that you can have this, you have a slight bump that comes from that initial enhancement, but you can also have a dip behind it because you lose more than you gain from in this location than you gain from the diffusion. And that means that you will never reach monotonicity. And so this changes about how I think whether radial diffusion is still interesting, like real radial diffusion, not our idealized version in some of these experiments, but it also means that the time to monotonicity is maybe not so, it needs adapting to this. So to wrap up, one of the two things that set this off was a simple question of, oh, but the diffusion coefficient depends on else. What does that mean for when things are at higher L? And actually, this seems to affect quite a lot of things. And one of the more important ones appears to be the outer edge of the domain, right? So I could probably have done a whole talk on just that and how to choose what that should be and where we are at the moment. But we to answer that more, we've now got some tools that we can use to understand that better, like the analytic quantities, and we also have some more understanding about how to analyze ensembles. So I just wanted to highlight that we're really going to need this 1/L² factor, otherwise you're not capturing it's just not, you're not getting all the relevant information. So like a mean square error or equivalent wasn't relevant to us, but it might be to other applications in future, but you'll also need to include this. The time to multiplicity is quick and intuitive, but we not quite ready for loss yet. The analytic tools are really useful. Downside of that, you need the slightly idealized diffusion coefficients. But if you use the rate of change of the energy light density, that raises some questions about whether we can simplify it to radial diffusion, and whether we should be looking at the gradients of the system. And that part is still, we'll hope to answer that part at some point. Right, so yeah, thank you for your attention, and hopefully I ran over a little bit.